Yes,
Yeah.
but where is it storing? It did not ask me for local or cloud.
I think it will store in your local only right now.
Okay, let me check it out. Okay, so let's proceed with our discussions ahead, and we'll discuss more about it.
Hey, Ankit, I have a follow-up question on the things that you just said right now.
Sure.
You said as Prometheus could be too big or it has too much load. How do you quantify that? Like, what is too much load? How is too big? I got that metric of 100,000 is good enough to store. So that's kind of like a rule of thumb, I guess. So if you have more than that, probably you should think about storage. Currently, we are just using disk storage. It's not actually having any issues for us. But I want to understand the too big and the too much load for the high availability.
Right, sure. So too much load in today's term, like if we are using EC2 instances, the prices scale linearly with the number of CPUs and the number of memory you add. But generally, it's not the case. The vertical scaling is more difficult to achieve than horizontal scaling in terms of cost. Okay, and in terms of availability, like in one machine, you can scrape, you have to increase the CPU resources and the memory resources again and again. So it's a critical problem. Like how would you like to design your system to be horizontally scalable or vertically scalable? Okay, and when you set, let's say your Prometheus scrapes everything in 30 seconds, every time change data in 30 seconds or 1 minute. Okay, now you have, let's say, hundreds of endpoints or thousands of endpoints to scrape, and you have set alerts that will notify you about any anomalies, and you have set alerts like hundreds of alerts. Okay, now those alerts rules will be evaluated every minute. Let's suppose you have now 100 alert rules, so every minute or 30 seconds those 100 alert rules have to be evaluated. So, and it should, and the time to evaluate those rules should not be large, so that the alert times out, like when you have the metrics and you try to apply those rules, it is not too late, right? Because everything has to be concurrent to achieve that. Okay, so this is the risk. So first thing that as a user you should observe is that the response times of the typical use cases and the alerts that you have should be under your control. Like if you want a 1 second or 2 second or 5 second delay in your alerts, that you should be able to control. If you see the response times in loading the charts going to more than 1 minute, then you need to think like the load is big enough. Another thing that can happen is that Prometheus scraper. So Prometheus tries to go to each and every endpoint and tries to scrape those metrics. Okay, so those things will start timing out if you do not have sufficient resources. Okay, so you need to observe these things, like if there's a famous problem with out of memory problem with Prometheus. So if you scrape all these points, and first there are two times, writes and reads. So scraping all those endpoints or time series and writing to a disk, you should be able to monitor the CPU and memory usage. How is the profile do? Like, so do they have spikes in usage? And once they are writing, your read capabilities are at the same time being compromised, right? So the things are limited. Now on the read side, let's suppose you are evaluating those 100 rules again and again every minute, then the read performance will be minimized. And if you see that your queries are timing out and they are not replying within a given amount of time, then you have to optimize for this system, right? So then that's these profiles you have to monitor before thinking that you have to increase the resources or like that. So, but if for a small setup, if everything is working fine, well and good.
Cool. Thanks. It's more like having an observability of your observability layer. That's what you're saying.
Right. So you anyways have to have some sort of about your observability, like whether they are working at all or not, right? So you can even have another Prometheus to scrape the major Prometheus that you have. So even if people say that it does not make sense, like a Prometheus to Prometheus and again a Prometheus to Prometheus chain, but what happens is that the probabilities of going down reduces. So if let's suppose this is the blast radius of this Prometheus service going down, try to keep it in a different region or geography, the other Prometheus setup that tries to scrape this Prometheus. So there should not be like the probability of going this down is 0.1%, and if the probability of going this down is 0.1%, then the probability of going down the overall system will be 0.01%. Right? So think in those terms.
Sure. Thanks.
Welcome. Yes, so we'll get started with observability and distributed tracing problem. Like for the beginners, we'll get to a few amount of basics, like what is observability and what is distributed tracing, why distributed tracing is picking up, and why it is important in microservices world. Right. So the observability, as we have heard, is like it's like we try to it came from the word like observe. So we try to observe a system from outside and want to know, like we try to find out how its internal states are and how things are there, right? So as an example, like if I see a few different things from the outside world and I want to know what is inside, that's observability. Like if you are seeing a person, you're seeing him sad, you should be able to tell him from the internal states, like he is at a pay skill cut, he is not well, or something like that. Similar analogy goes with a thermometer to measure temperature. So rising of temperature is just a indication, like it's just an external output, like we observed an increase in temperature. But what was happening inside, the raise in temperature is due to malaria, dengue, or any other thing that is the root cause, or that is the internal states of a system or of a human, right? Similar to in our DevOps world or the infrastructure world, we can say we observed an increase in latency of our endpoints. So what is the internal states of different machines and the applications and the databases that are being used that led to the increase in the latency of that endpoint that you observed? Okay, so those are the internal states that you should be able to figure out. Okay. There can be various points of failures when it comes to increase in latency, like it can be due to the memory hogging or CPU hogging of resources, or the database has become slow due to some other reasons, like if anyone is using that topic or partition more, it can happen due to various reasons. Right. So that's the overall concept of observability. Now we have to think like why observability has become so important today. So it was out of question 5 years back. Now everyone is talking about observability. So fundamental shift in the architectures of our system has happened in the last few years. We have moved from monolithic to microservices world. In monolithic, all our applications used to run at the same place. Right now, different business logic and functional components like reads, writes, you have customer service dashboard, you have driver partner dashboard, you have customer facing dashboard. Everything used to happen in the same set of monolithic application. But now that changed to microservices. Like we tried to divide all of these into separate individual components and systems, and they interact with each other a lot. Like when you load a Flipkart or Amazon web page, you go through multiple services before seeing the results. Like you go through product suggestions, recently viewed items, recommendation service, cart service, or the list of catalog service, and all these services interact with each other before giving you the same set of results. This increased the velocity, or the microservices architecture increased the velocity of the development. Like each microservice or business logic is independent and they can choose their own stack. So if something is write heavy or something is read heavy, they can use different languages and stacks or databases to interact with each other. And so the best thing I like about microservices is that each and every individual component of can be scaled independently of each other. right? So in our case in SigNoz also, we have writes and we have reads on the other hand. If we have to increase the amount of writes per second that are happening into SigNoz, I just increase the number of receivers or the collectors or the component that is responsible for the writes, right? We just need to increase that. We don't need to change the query layer or the front-end service layer or something like that. But that's the beauty of microservices. Now, if we have to debug something, monolithic was simple. We have a lot of set of debug statements, not many of the interactions between services happening, not many network calls between inter-service communications. So we can have a set of tools that we can plug it in there and get some data out of it. But in microservices world, as clearly depicted in the picture, we have a hell lot of devils and demons running, which can fail and which can go slow due to various reasons. Now, which of them is interacting with which others of them? And if anyone goes slow, what happens to all the dependent services? So it becomes very difficult to figure out the root causes. Okay, so now where to put the observability tool to figure out what is the root cause? Okay, so now we need to have some sort of mapping between the request, like where it is going, and so we have to have some cohesion or correlation between the data between different services, so that we are able to drill down them better. So the three pillars of observability, as we discussed, are metrics, logs, and traces. Okay, so metrics is anything that you can measure or you can aggregate. Okay. So like if you are counting the number of steps you have taken in a day or the number of breaths counts that you have taken in a day, so everything comes under metrics. Metrics is an aggregate. So if you are checking about the average latency of your application or the 99th percentile latency of your application, the amount of requests handled per second or per minute by your application, the error rate, like what percentage of your requests are sending out errors. So everything is an aggregate and it comes under metrics. And Prometheus has been a very gold standard for metrics for the last few years. So Prometheus gives you the ability to scrape some endpoints and collect those metrics, and the ability to give you a server or a server where you can run your Prometheus query languages, like you can do the various sum, averages, max, min. All these operations are supported by Prometheus query language, which we call PromQL. So, and apart from that, Prometheus gave you alert manager. So all these are gold standards that has been given to the market by Prometheus. Okay. With logs, we have been familiar with our age-old days. Like it's like emitting an event at any execution step in your application logic. So if you are step 1, step 2, step 3, we can print different states or variable values and something like that to debug how things should be looking if you have to look down again when there's an issue in the production or when there is an issue. Okay? So we typically use open source tools like Elastic to deal with indexing or string, because logs are plain text, right? So it needs to handle a lot of indexing. So Elastic has been used in the last few years as a central storage for logs, and visualize it in Kibana. Okay. And the interesting things about logs is that due to the unstructured nature, like it's a plain blunt line of text, it becomes very inefficient to store the data into disk, and we have to do all sort of indexing techniques to optimize it. The world has been moving toward structured logs. Like if we are able to provide some structure to logs like key value pairs, then it becomes very efficient to index by those keys and search by those values. Like a few standard things in a business can be very specific. Like in a technology, we can have key value pair of application name, like application name, endpoint name or API name, the time taken, or different parameters like the log level. All these key value pairs can be extracted out and can be efficiently stored. Right. So this has been moved. The world has been moving towards having more efficient and structured logs, so that it becomes efficient and cheap to store. Now, tracing became popular in the last few years, roughly from around 2015 and 16. Like it became with the need of monitoring things in a microservices world. So what tracing does, it tracks down the request from the incoming or the first point of contact with the tracing system. It starts there, it starts tracking that request there. Then as the request goes through service 1, service 2, service 3, service 4, and down to a database call, and it gives back the results to the user, it propagates the data across the services and keeps on adding some data or observability data that we need, right? So that helps a lot in like debugging things. Like, the correlation between the upper services, the downstream services, and the sequential execution of the steps. If you have to figure out like about any key value pair or any other specific requirements that you have about debugging, or to know more about that particular kind of request, like even simple like a browser based request. So if some of the requests are failing in a particular kind of browser or a particular type of customer that you have defined, you should be able to figure all those requests out and debug it. So logging is just a blunt line of text that is going through execution, but it becomes very difficult to manage logs because a lot of 100 lines of logs can be executed at a very fast rate and concurrently, and it becomes very difficult to find the correlation between log line 1 to 2 through 3 to 4. So that sequential execution of events tied up together is tracing. The basic terms of tracing are the trace ID or the spans, or the span ID. So all the spans, span is basically an individual event. So any event that is executed as part of tracing, a tracing tool or tracing system, is a span. So the span can have many data that you can write out. So by default, like it has the start time and end time, the duration, the service name where it was executed, and the name of an event. So these are the basic information that are automatically written to an event, and we call the minimal unit of event as span. And when we collect or do a logical grouping of all these span IDs that are associated to one single request, it becomes a trace. So one trace is equivalent to one request, and that trace can have 50 or hundreds or thousands of spans underneath. Okay. So this is a typical example of an Uber architecture, like how the different services interact with each other. So service 1 goes to service 2, service 2 to service 3, and it goes to a lot of services before getting the result back. Now, it becomes very important to find out which services are down. Like if I am the owner of service A, and if my services are failing, I would like to know whether it is a downstream dependent services which are failing or not. Like in my earlier startup, there were 8 services dependent on each other. And if one service was broke down, people used to shout on each other, like your service is breaking and your service is breaking. Like, so there's kind of conversations happen between teams. So as a service owner, I would like to know whether the downstream services on which I am dependent are working fine or are they breaking, right? And now these applications are deployed into different machines, and multiple replicas or availabilities of those instances are also there. So we want to find out like which instance is it breaking. Is it due to application or a specific type of request that goes into that machine, or is the machine resources hogged by due to some other reasons? So we want to find out all these reasons. Now, a very important and useful case becomes when we try to deploy our systems or our applications every 1 week or 2 weeks or multiple times in a day when we have CI/CD integrations. Right? So with every deployment, we like to know whether this current version of deployment is giving you more errors or is slow as compared to the earlier deployment. So that's the baseline that we compare, like earlier deployment was working fine, and now the newer deployment version is giving you errors or is slow. So we need to find out or answer all these questions while we debug the systems. So now we'll talk more about OpenTelemetry and why is it important. So OpenTelemetry is a vendor neutral instrumentation library. So it's a set of toolkit including SDKs, APIs, and different libraries that help you instrument your applications. Right? So it's simply a data generating tool, and gives you the flexibility to write your own data or to send out your own data from your application. You can import the packages of OpenTelemetry, and you can write your own set of events, so you can generate your own set of metrics and logs. So OpenTelemetry comes out to be a vendor agnostic. So the problem of, let me go deeper into the problem of being a vendor neutral, or why is it vendor agnostic is positioned out there. Earlier, we used to have SaaS vendors like DataDog or New Relic, which would give you a set of libraries to put inside your application so that it starts sending data to DataDog, which you later go into the UI of DataDog to see the events in beautiful dashboards, right? So the data generating part is taken care by the set of libraries that you put into your application. Now, as you grow as an application developer, a team, and an organization, you start writing code using the DataDog libraries to start generating more and more data, your custom business specific data, or your anything that is specific to your business or your tech stack. Now, after a few years, 4 or 5 years, when you go down and you see the DataDog bill exploding a lot, you want to go back and change your vendor from DataDog to some other vendor. But when you go back to your code, you see everywhere there is instrumentation already done using the DataDog libraries. Now, as you remove the DataDog libraries from the dependencies, all these lines will start giving you errors. So shifting from DataDog to other vendors becomes like kind of a migration plan. And hence people stop doing that because it is not centric to their business idea and needs, so they keep paying to DataDog. So this is the problem of being sticky to becoming sticky to one specific vendor. Now, what OpenTelemetry did is it open sourced all these libraries that generate these kind of data, metrics, traces data, traces data, and logs data. Okay, now since you are not dependent on any vendor, you can freely write your code in OpenTelemetry. Okay, and you can choose different vendors or different open source tool to start sending your data from OpenTelemetry. So that OpenTelemetry has given you power to choose your exporter. Okay.
Hey, Ankit, you're muted.
Hey, Ankit.
Ankit, we can't hear you.
Sorry, man. I was drinking water, so I muted.
Sorry.
We'll go back. So these OpenTelemetry libraries give you the ability to create data and collect data into something called OpenTelemetry Collector. We'll go deeper into OpenTelemetry Collector very soon. Okay, and OpenTelemetry supports a lot of languages and frameworks and libraries inside those packages. Okay, so it's for Java, it supports It supports Spring, Tomcat. For Node.js, it supports Express. For Python, it supports Django, Mongo, PyMongo libraries, or anything you can think of. So OpenTelemetry is based on open source model. So it develops code to instrument those libraries, and it gives you the ability so that you can start measuring them. Now as we know, it's open sourced. So OpenTelemetry is only relevant for creating the OpenTelemetry data, creating the telemetry data or the tracing data, the metrics data, and collecting it. Let me tell you how OpenTelemetry instrumentation actually works. Let me actually browse through the OpenTelemetry website and give you some glimpse. So this is the OpenTelemetry website. It has support for Java, Golang, JavaScript, Python, Rust, C++, Erlang, Elixir. Okay. So it's a CNCF project. It's a well-known project. Okay. Now what we'll try to do is it also integrates with popular frameworks like Jetty, Kafka, Django, Redis. Let me tell you how it actually works. So we'll go to OpenTelemetry Python, let's suppose. So if you have to instrument your Python applications, you will have to go to OpenTelemetry Python to look for instructions to how to do it. Okay. So when you go to OpenTelemetry Python, you will have a different set of ways to install OpenTelemetry API, OpenTelemetry SDK, and OpenTelemetry instrumentation. Now we'll go down deeper into OpenTelemetry instrumentation. So this is the contrib repo where it has instrumentation packages. And here we can see it supports a list of many different packages that you use. You use Flask, Fast API, gRPC, Django, Celery, Redis, Pyramid, PyMongo, PyMySQL. So URL-lib3, URL-lib, UWGI. So these are all the instrumentation libraries that are being supported by OpenTelemetry. And what does that mean? So if OpenTelemetry is supporting Redis in Python, it means since Python, your application code internally calls Redis by doing some sort of internal call that uses the internal functions of the open source code of the Python Redis client. How will you do a normal Redis client call in your application? You will import Redis. Let's suppose a MySQL. For MySQL, you will have PyMySQL, right? PyMongo, PyMySQL. These are the client libraries that you import in an application to connect to the database, to write SQL queries to the database and all, right? Now, OpenTelemetry, since these connectors or these client libraries are open source, so OpenTelemetry knows which function at the end are executed to send data or to request query to the MySQL server. So it knows which functions from the client libraries are used. So it patches those functions. It puts a hook around those functions and notes some information like now Redis calling is being made. Now the start time is this, a service thing that you have already provided. And after the call has been made to the server, then it comes back and the callback now it writes like the time for the MySQL call has ended, and this is the event name that I am supposed to do. This was the query made to the MySQL. So everything around that function call, it tries to hook into some of the data, right? So this is how instrumentation works for everyone. The DataDog libraries, the new Relic libraries, all the vendors or everything you can think of work in the same way. They try to patch the functions that are called in the bottom line or at the end to do an exact call to the underlying resource like MySQL or Redis. So this is how it works. Now we have a better understanding like what kind of thing, what it means that OpenTelemetry supports a language or supports Redis or MySQL or not. Okay. Let me go back to OpenTelemetry. Yes. So now it says we support Redis, MySQL. So it has written some code to automatically patch those function calls, and it will try to give you some telemetry data about those calls being made. Okay, that's what it means. Okay, coming back to slide. Yes, now we understand what OpenTelemetry is. It is a list of APIs, SDKs, and libraries that you can instrument your application with to start sending some data. Now, OpenTelemetry has also given you the first level of collector. A collector is something that collects OpenTelemetry data. Okay. Now collector has three components. It has receivers, it has processors, and it has exporters. Okay, so let me go into the GitHub repo of OpenTelemetry Collector and try to understand what is happening there. Okay, so this is a generic information about the repo and all. So as I said, it consists of three components. Like it has a receiver, it has a processor, and it has an exporter. And this is OpenTelemetry Collector, means it collects the data about OpenTelemetry from the libraries that we talked about earlier. Okay, now receiver of OpenTelemetry Collector can receive data in various formats. So it has been so much modular and extensible that they have made it able to receive data from different formats. Let me go to the receiver folder and try to see what things it can receive data from. Jaeger is an distributed tracing backend that is used to visualize the data or the tracing data. So we can receive, so OpenTelemetry Collector is a single Golang application that you can think of. It will have a receiver component, a processor component, and a tracer component and an exporter component. The receiver component can receive data in different formats and from different sources, like it can receive in OpenCensus format, it can receive data from Kafka, it can receive data from Jaeger, it can receive data from Prometheus. So if you have set of Prometheus endpoints exposed and you have a Prometheus config, you can give that config to OpenTelemetry Collector and it will scrape those endpoints and it will send you the data. So it has also a Zipkin receiver. Zipkin was an earlier version of tracing receiver or tracing tool, tracing backend that we can collect or visualize the tracing data. So OpenTelemetry Collector now can receive data in Zipkin format or Jaeger format or OpenCensus or OpenTelemetry or any other format, a Prometheus format. So this has given you the vast capability to make it very much useful. And same things happen at the time of exporting. So OpenTelemetry Collector receives the data in these formats. It internally converts them into a format called OTLP. So OTLP is a new format defined by OpenTelemetry itself that it is using internally to process and export the data. Now, it received OpenTelemetry received format in different formats, and received the data in different formats. It converted into OTLP format. It went through a set of processors. So it has the ability to give you the capability to run some renamings, or you can drop some labels or something like that. So you have a set of processors, you can batch them, or you can try to drop some samples. So it has a few capabilities that we can have a look later, but it receives and it passes on to the different processors. And at the end, there is one exporter. So that exporter now can send data to different plugs or plugins that are available. So one of the plugins can be DataDog. So now OpenTelemetry Collector can receive data. It can collect, receive, and export the data to DataDog. You can, at the exporter, you can have even multiple exporters. Like you can export to Prometheus to visualize. You can export to Jaeger, Zipkin, or any other format. Okay. So let me give you an example. Like you can receive the data in Zipkin format. So if your applications have already instrumented using the Zipkin libraries, the OpenTelemetry Collector will receive the data in Zipkin format. It will do some sort of processing, and it can export in Jaeger format to be visualized in the Jaeger UI. Right? So this is very much pluggable and configurable. So this is the receiver repo that I have been talking about. Now let's have a look at the exporter. So the exporter is like you can go to a file, you can use a file exporter, it will write all the data into a single file that you can just use it to test and play. Right? You can write it to Jaeger so that you will run Jaeger and you can visualize in the Jaeger UI. You can export it to Kafka where you can have different systems plug into Kafka and take the data and do some sort of processing and do whatever you like. This is logging exporter. This will just log the output to a console. It will not do anything. It will not send it anywhere. Now we have OTLP exporter. This OTLP format that I talked of, it will export in the same format to any other source that can receive in OTLP format. Like one OpenTelemetry collector can send it to other OpenTelemetry collector, and Prometheus exporter and Zipkin exporter and all. All right. Now it has some sort of processors that you can use. This is the processors. Sorry. We have attributes processor, we have batch processor, like we can do some sort of filtering and we can change the attributes and drop the attributes. Some sort of sampling processor is also there. But these are head-based sampling rather than tail-based sampling. It will be a bit deeper subject. We can discuss that later. You can ping me out anywhere and we can discuss that. So it has some sort of processors like generic processors that can help to change some amount of data that we receive in the OpenTelemetry. So that gives you the basics of OpenTelemetry and what OpenTelemetry Collector is. So OpenTelemetry together gives you the set of libraries that you can use in different languages and has support for different packages that you use like Redis, MongoPy client and all. OpenTelemetry also gives you a collector that can receive data from different sources and different formats, and you can convert them into different formats. But OpenTelemetry does not give you a backend. Like OpenTelemetry Collector can export the data to some other tools, right? And that tool or backend should be able to collect these data to analyze or as needed. You should be able to store those data, and it should be able to have a UI to visualize those data. Now, some of the open source tools that we know are Jaeger and Prometheus that can visualize these data. And DataDog is a SaaS vendor that can visualize this data. Okay. So DataDog completely is a SaaS backend that can ingest this data and store, visualize, and see this data. Now, SigNoz is an open source alternative to DataDog. So whatever DataDog does, we are able to do it, what we plan to do it again. So we can receive data from OpenTelemetry Collector, store it, analyze it, and give you a beautiful UI to see all those data. So now we have also OpenTelemetry Collector contrib repo, which has some different functionalities that you would like to achieve later on. Right? So let me give it has a set of receivers which can receive data from different formats for different use cases. Like now, if we need to have Redis metrics data, then what we generally do? We have a Redis exporter in Prometheus. Like the Redis exporter exposes the internal metrics of Redis into an endpoint. Prometheus scrapes those endpoints and it stores there, or it sends to a remote endpoint. Now, everything can be abstracted away into OpenTelemetry Collector. OpenTelemetry Collector now has a Redis receiver. So it should be able to, if you can give the credentials of Redis or the permissions of Redis here, this OpenTelemetry Collector should be able to read the director directly from Redis and propagate it into its processors and exporters. So this gives you a very seamless service. Similarly, we have Nginx receiver, Prometheus receiver, Kubernetes cluster metrics receiver, Kafka metrics receiver, JMX receiver for Java applications. So these are the different accessories tools, I would say, that we can use to get more data from your infrastructure and applications. Okay, cool. So let's take a break and then we'll discuss more about SigNoz and how to, now we since we know about OpenTelemetry, how we can actually use OpenTelemetry to instrument our application. We'll try to run it in our own laptop or machine that we have, and we'll try to visualize and go through all the data and we can play around with it. Okay. So stopping my screen share, we'll get back in 10 minutes. Hey folks, if we have any questions, we can take that up and before proceeding to the next session.
Okay, so the collector, right?
Yeah.
How does that run as a separate process and then like sort of export it to various like backends that we want to configure, or like how does it work?
It's like an independent application. If you are using Docker Kubernetes, you will have an independent image that you can run.
Got it. Okay, it's like a sidecar sort of a thing.
Yeah. Like, I can show you. Yeah, cool. We can proceed with the rest of the session. So we'll try to understand why we build SigNoz and how's the architecture of SigNoz, like we'll install SigNoz and try to play around with the data, and we can try to instrument one application and see how it works. So as we have seen that OpenTelemetry gave you a single unified way of generating metrics, trace data, and logs data all from a single OpenTelemetry package. So, and OpenTelemetry can collect in an OpenTelemetry collector. The backend is still missing. So to use open source backends, you will have to plug in Jaeger along with the other Jaeger components to collect the trace data from OpenTelemetry collector and see it in a Jaeger UI, or you will have to use Prometheus to collect the metrics data from OpenTelemetry collector and see it in a Prometheus UI. So these systems now are independent of each other, and the UIs are different, and the query service are different, and everything is, the separate pipelines are also very independent. The database is also independent. It is completely independent of each other. Now OpenTelemetry is going into alpha version of logs also. Like with the same package that you imported, you can have log lines. You can write something .log or .info or something like that, and that will again give you that capability to export everything from a single library into single OpenTelemetry collector and use something at the backend for logs. Right? Either you can send all metrics traces and log to vendors like DataDog, or there you can use independent tools like Elasticsearch and Elastic and Jaeger and Prometheus for independent verticals. Now, with SigNoz, we wanted to be a single unified open source backend for OpenTelemetry. So you should be able to send data from OpenTelemetry collector to SigNoz, and SigNoz will take care of storing, visualization, querying, and everything, and scalability that DataDog internally does. Apart from that, we use OLAP database, that it is an analytical database, of you can say column-oriented database. That gives us the capability to run aggregations on the trace data. What we mean by running aggregations on trace data is that right now, in the existing tools of Jaeger and others, you can just see a single trace, and by trace I mean a single request. Okay, and the different events that it has underlying, you cannot run different queries on those events. Like, let's suppose one of the events in one trace has a key value pair like instance ID or channel partner or customer type is equal to gold or something. I would like to know what is my error rate for my customer type is equal to premium or gold. And I would like to have a separate alert for my premium type customers rather than open source or free type of customers. Right. So these capabilities are not there in tracing data due to the usage of the databases that we are using at the backend. So Cassandra, Elastic, though they're evolving to have more of analytical capabilities, but by nature of the design, they are meant to handle different things. And OLAP databases and liquid databases are meant to handle aggregations and filtering at huge scale, like billions of data points. So right now we support ClickHouse and Druid as the OLAP databases, and they perform fantastic. And by virtue of them, we are able to provide powerful filtering of traces. Like when we have list of requests, you would like to have some filters like which request to look into and which request not to look into, and run some aggregates and give me some latencies and errors on those filters. So these kind of capabilities we are able to provide. Now with the simple open source, as with any other open source tools, they come with a disadvantage of time to set up those things and the difficulty in maintaining those at a scale, those open source tools at scale. Like Prometheus itself takes 1.5 months to set up completely in like enterprise scale with exporters and the HA availability of Prometheus with Cortex and everything. It takes around 1.5 months to just set up the metrics side of Prometheus, right? So we try to be, and on the other hand, SaaS vendors like Datadog and Relic give you completely things out of the box. So we are trying to bridge that gap. Like we would like to have some operators or scripts or any things that can make the life of running open source tools easier. But that is in some later part of the journey. But sure, that is a big concern for us. Right. So another aspect as we were talking about is like, since it is open source, you should be able to run it in your own infrastructure. And that can help you in two ways. First, it will be a lot cheaper. So we did a cost benchmark, like it was easily a 1/10 of the price of the charge that Datadog takes to store traces. Right. So it will be much cheaper. You don't, so since Datadog has just 20% to 30% of infrastructure cost, and the rest is their marketing and their profit sharing and everything. So if you run it in your own infrastructure, it will just be your infrastructure cost. And the second one being, since the data will be remaining inside your own boundary, it will be very much in your control. So you will be able to govern your data in a much better way, and you don't have to face audits like audits for security and privacy for purposes. So these purposes in mind, we are building SigNoz as a single unified tool for observability. Now, the architecture of SigNoz is something like this. Like as we discussed, we have applications running in your infrastructure. Application 1, 2, 3 will have OpenTelemetry libraries here inside your applications installed that will start sending data to OpenTelemetry Collector. Now, this OpenTelemetry Collector comes in the boundary of SigNoz. Though we can have multiple OpenTelemetry collectors inside in each machine of in each machine of your infrastructure, that OpenTelemetry collector data that can collect data more about again from your applications and about the host data like CPU usage, memory usage, disk usage, and all. And OpenTelemetry Collector has the ability to send data or export data to another OpenTelemetry Collector in OpenTelemetry or OTLP format, as discussed, right? So these applications with OpenTelemetry libraries inside them will be sending data to this OpenTelemetry Collector directly of SigNoz or the intermediate OpenTelemetry collectors. And those OpenTelemetry collectors will be sending data to OpenTelemetry Collector running in SigNoz. Now that OpenTelemetry Collector will export data into ClickHouse, the database that we are using right now, or it can be Druid. ClickHouse for the long-term storage, we can write to S3. Yeah, so that's become very S3 is very cheap and performant and robust when it comes to handling blob data or similar data. Right, Thanos uses S3, and other systems are also moving to use S3 as a cheap, efficient storage. Now, the hot data that you need to load, or the recent data that you need to check regularly, will be in the disk of the machine that is hosting ClickHouse. And the older data, like more than a month or 2 or 3, that you can set in your application, like how long data you want to keep it in the hot load inside your disk in ClickHouse, or you would like to write it to S3 for longer term retention that seldom you want to like to bring it back and check it out. Now, once we have written the data to ClickHouse, we'll have a query service that reads the data from ClickHouse, and it talks to the front end to display the UI. Now, this system is modular, right? So we have, this is the write part and this is the read part. If we have a lot of increase in the writing capacity, so we can increase the number of OpenTelemetry collectors that we need, right? We don't need to increase the query service layer or the front-end service layer. Now, again, if we have a lot of read functionalities coming from the front end, we can increase the query service layers. So this is horizontally scalable, right? So these are the basic components that we have, like OpenTelemetry Collector that receives the data in the first hand. Then it has ClickHouse. Then it stores the data. We have query service, which queries data from ClickHouse and interfaces to front end. And the front end is the React UI that we can see. Okay. Now let's try to run a SigNoz in our laptop and see how it works out. Okay. So I hope you are able to see my screen. So we'll go to SigNoz installation docs. We have a deployment with Docker and Helm chart. The Helm chart still uses Druid, and the Docker one uses, we have an option to choose between the different kinds of setup. But for low memory footprint, I would suggest to use ClickHouse setup because it takes less than 1 GB to set up. But Druid and Kafka setup is will be able to handle more scale due to Kafka, but takes around 4 to 5 GB of your machine of RAM to run. So we'll do git clone of this repository of SigNoz, and we'll go to the deploy folder. So if any of you are trying it out, feel free to ping me if there is some error, or if you are using it later, feel free to raise any GitHub issues that you find well. Okay. So we just do git clone and we go to the deploy folder. And inside that folder, we have an installation script that gives you option to choose between ClickHouse setup and Kafka Druid setup. Then you can choose either of them, and it takes care of. So if it expects you to have Docker Compose and Docker, but in Ubuntu, I guess, and the other systems, that if you don't have Docker and Docker Compose, it also installs them. But I would suggest if you have Docker, you start your Docker up. And if I'd suggest, if you're using Mac, you install Docker and Docker Compose. I hope most of you would have this ready. So just feel free to stop me at somewhere and ask more about it. So this is my SigNoz folder, and we'll go to deploy folder, and we'll try to run /install.sh script. So this is my local Mac machine. I hope it should be installed. So when we run this script, it asks me to choose a setup, ClickHouse and or Kafka and Druid. So we'll go with ClickHouse since it's much less on resource requirements. Now it should pull some Docker images and try to start containers and all. I'm over 8 GB of usage. We have less of RAM. So to stop a few things. I guess Zoom is taking a lot of memory. So let me spin up a new EC2 instance and then we'll try to deploy it there. In the meantime, you can try to run it in your own machine. So pulling the latest container images for SigNoz. Let us check again if this works on my local. So it is downloading images of ClickHouse, query service, front end, OpenTelemetry Collector. These are the 4 images that we need. And we have a hot rod service that is it's an application that has inter-service communication in between. It's given by folks from Jaeger when they built Jaeger as sample service. And this load hot rod is, we are trying to send load to this application so that we have continuous data to look into in the charts. So if you want to have a look at this hot rod application, so this is the application, sample application that we'll be looking into. So it is a ride on demand, like something like Uber. When we click on either of these UIs and the buttons, it will try to order a cab. And internally, it has 4 services, I guess. It is front-end service, the driver service, the router service, and one more service. And they internally talk to MySQL and Redis. These are simulated databases, and they try to communicate with each other and try to give the data back to the user. So when we click on either of them, so we have something like a driver, this is arriving, this cab is arriving in 2 minutes. So it goes through a lot of services internally. So this is the architecture that the front end gives call to the front end API. It calls the customer service, and customer service has MySQL. And these front end service calls also calls the driver service, and it calls the route service. So this is the I would say the service map or the architectural diagram of hot rod application, and we'll try to run this same sample application into ClickHouse, into our SigNoz setup with ClickHouse. Now, as we see, it was pulling the Docker images, and it is created images and the installation is successful. Now the UI is visible here. And if we have to bring down SigNoz, we need to run this command docker compose -f docker / ClickHouse setup -docker compose down -v. -v removes the volumes or the data used by ClickHouse also. So you might want that if you want to completely uninstall the data also, right? So the installation is successful and it's complete. And let's go and have a look at our localhost 3000. Yes, this. So let's have a look at the dashboard, and there are 4 applications right now that sends data, data services that the hot rod I showed you the example application has. This is a front-end service, and this is a customer service, this is a driver service, and the route service. So we try to simulate, like we try to give you a dashboard completely like an APM solution like DataDog. So here it shows the P99 latency of these applications, the error rates, if at all these are coming by, and the request per second that this is handling. Now, since we have already run the load hot rod image or example, so it is continuously generating data to hot rod application. If we do docker ps, we can see the list of containers that are running. Sorry. So we see SigNoz frontend, SigNoz query service. This is the hotel collector that we are running. This is a ClickHouse server. Now we have this locust. We are generating data using the locust tool in Python. And this is the example hot rod application that we are using to display. Now, since we have these P99 latencies and all these RPS and error rate and P99 latencies and the different applications, let's go deeper into any one of the application and see what is happening there. Let's choose a front-end application. Right? Now, this will give you like the P50, P95, and P99 latencies of this particular application of front-end. So this is the 50th percentile, like how the 50% of the users will be experiencing the latencies, and P99 is how the 99% of the users will be experiencing the latencies. So if P99 is greater than your threshold, specific threshold, then you should be drilling down deeper into it. Okay. Now we have request per second. We can see the RPS. So since we just have installed this setup, so the data won't be longer than 2-3 minutes, maybe 1-2 minutes. So it will keep on generating the data, right? And we'll have a continuous graph and more amount of data, like it's L136 to 39, only 3 minutes of data is there. Now it's L139. So if we keep it running for 1 hour, then we'll have 1 hour of data. Here we see the RPS, and the top endpoints will also be able to see like what are the APIs exposed by this service front end, and what is the latency profile and the number of calls being made. So if you see any particular endpoint being slow, you should be able to know that from here. Now, similarly, we will be able to see the error percentages and how it is varying over time. So now let's have a look at now when you go to different data points present in this graph. So these are very small tiny dots out here, which are the data points actually, and the test is interpolation of that data points, right? This is 1 minute, this is 1 minute data, right? So if we want to drill down deeper into this data, like what is happening out here, if you feel the latency is high there, we'd like to drill down deeper, then you would like to click on this one and go to view traces. What it will do is it will take you from metrics to the paradigm of traces. Now traces, we can do a lot of different things there. Okay, let's click this. So we have come from metrics tab to the traces tab. So this has automatically selected the service name and the time range in which you were interested. Like if you saw a peak in the latency profile during some particular minute and you'd like to see what was happening out there, then you can click on that time button, range button, and you can select this one and you can come here. Even in this one, you can set out custom started and date and the time, and you will be able to filter those traces out here. Now, here, this is an option of all the endpoints or the event names that are associated with this service. Okay. So these are the events. You can choose any of them, the events, and you will be able to see these are the list of spans that are associated with the above filters. So if you choose, if in the list of all the data that you're getting, you get the service name front end, that and then choose the operation name or the event name as this, find nearest, you will be able to see all those events and the duration in them, right? You can also do something different, like you can also choose to see what are all the events that are taking more than 1 second, and I would like to see all those events. Now we got only 2 events that are more than 1 second. Okay, so let us go to that particular event. When we click on this, we'll see the list of all the spans associated in that particular request. Now this is one particular span, right? It was one particular event. Now a request has traveled to multiple services, and multiple events in each services were emitted to constitute one particular trace or one particular request. Now this is one particular event that was called when the /dispatch endpoint of front-end service was called and had a time of more than 1159 milliseconds, right? 1.1 seconds. Now we click on this, we get to see the complete trace or the complete request, what happened to the request when it started the boundary. Now we see this is selected, means /dispatch endpoint was clicked. We go down and we see then this customer service /customer endpoint was called. So the before the colon is a service name, and after the colon is the name of the event. Okay. Sorry. So this service name, this service emitted this event, and these all events are in parallel because they are the same child, they are the same siblings of this parent, right? So this parent took 1.1 second, as we are seeing here in a timeline, and this /customer name event name was taking 5 seconds, and this event find nearest is taking 200 milliseconds. Now we have some idea like which are, and front end is continuously calling /route endpoint. Okay, now we have a huge idea like what is taking most of the request time, right? And this is a complete request. Now we see /customer is taking most of the time. Now we want to go down, triple into this one. We expand this and keep on expanding the parent child like this. We see this front end /customer is calling front end /get, is doing a get request. It is going to a customer service, from front end service to customer service. The customer service is handling /customer endpoint, and it is underneath calling MySQL select query, right? And you see the front end, the first request here, parent request took 553 milliseconds, out of which 549 milliseconds was taken by the MySQL query, right? So you now somehow know that half of the request time is taken by the MySQL query. Now you want to know, now when I select this one, we get displayed a list of details about this particular event. Now we have some set of tags or key value pairs associated with every event, right? Now this event has service name MySQL, the operation or name or the name of the event. This is analogous to name of the event. We call it operation name in OpenTelemetry. It was SQL select. So SQL correct select query was fired. And in the tags, we can see the SQL query, the query that we was fired was select star from where customer ID square to score. So this is usually masked, but this is a sample application given by Jaeger folks using the hot rod application. So this is passing the customer ID, right? Now we know about this path. Now we want to see this path. Okay, so now I see there are 185 milliseconds, we have 199 milliseconds. We go and expand this. Oh, this is calling fronted service calling route service is taking 191 milliseconds. Got it. So our next is also /route service and it is taking 37 milliseconds. Now it becomes a bit overwhelming to see all these events emitted, right? So in total, we have around 50 events for this one particular request. It goes through front-end service, customer service, driver service, and all. Now this becomes a bit difficult to manage, right? Being a lot of events. Now, if you are interested in one particular event or span, you can select it and you can go to focus on selected path. What it will do, it will take you to that particular tree only. Let me do that. Now, after you selected on focus on selected path, the complete tree is expanded, the subtree is expanded, I would say. So we see here that it took 185 milliseconds and Redis service is called with find driver IDs. So it took 19 milliseconds. Now Redis is continuously calling get driver emitting get driver event. So it is trying to get driver details continuously like in a sequential steps. Why I'm saying sequential steps is that you can see the first request was sent like here, and when this ends, this was sent here. So it is making a staircase pattern, right? You can see. So it is continuously calling that get driver endpoint, and it's continuously giving me a staircase pattern, right? So when this ended, this is started. When this ended, this is started, and something like this. So this just calls are being made sequentially like a polling kind of thing. Redis get driver detail. Unless I get the driver detail, I will not move ahead. Right? So now I know how is this performing. Now I need to go back to my previous view. I would do reset focus and I get back again here. Now I can explore some other things and I can do the same, like select this one, focus on selected path, and I know, okay, these two are pointers taking 39 milliseconds, 38 milliseconds, and this is at the end of the timeline of the request. Okay, it doesn't matter. But here again, you can see the tags that are associated with this request. So it is calling an external URL, like it is calling another service with this URL, right? And it is doing an external call with HTTP status code is equal to 200. This is a similar view of flame graph. Like this is a flame graph that gives you an overall view of how all the events are gathered together, right? So you can see the /get dispatch point in front-end services calling multiple other downstream APIs. Like it calls this front-end services point, then again /customer endpoint. When you go and click on this customer part, it calls the same customer service /customer, then MySQL queries. Now, as you move along this one, this and the bottom line is automatically associated and the tags associated with that data is displayed. Now we do a reset focus. Now we see this, we want to focus on this subtree, like it calls find nearest endpoint, that called the driver service find nearest endpoint, and that driver service is doing the Redis calls continuously that we saw there. So this gives you an idea like how is if there is some anomaly in the pattern of your code execution or something like that, like is it the right way? So you get the overall architectural idea like how these things are happening, right? So this gives you some idea about how things are happening down there. This is about exploitation of one single request or one single trace. Let me go back and try to do something else. So what we do is we try to select the front-end service. So as we saw there in one particular event, there were a list of key value pairs. Now I want to run some aggregates. Now I saw those key value pairs. Now I want to run if in all the events that key value pair was generated, how is the overall time or the error rate associated with that, right? So now what will we do? We'll filter by tag key and value. The tag key, so this will search for all the events with this service name and which has tags that I give them now. Now, since the front-end service calls external or calls these internal services of front-end of route and customer service, we know that they are calling the APIs at port 8081. right? So this might be route service or customer service. Okay. Now what we are doing, we apply this filter. Okay. Now we are filtering all the events which have service name front end and which has a tag with key HTTP URL and the value this, right? So we are seeing all those events which is calling the downstream API slash with port 8081. Right? I can go back again here and I see this front end HTTP get is already selected and this calls the customer API. Now since this is already selected, front end HTTP get this event, we can see the list of key value pairs here. Now we can see the list of key value pairs is present, right? So we earlier filtered these events and we came directly to it. So this is the http.url with this number value that we put. The status code is 200. So it is calling customer endpoint, right? So customer and then customer service internally calls MySQL. Let me go back again. So we had front end, we had this, we applied the filter. Now I want to know that, yeah, okay, we got the list of events. We can go to individual traces or a complete list of traces and we can explore one particular request. But I want to know how overall it performs. Like I know it is calling the customer service and slash, it's calling a MySQL and customer service. So what is the overall, I would say, the P50 or the average time taken to call that customer service? Now, since we have the list of these spans, we have given this capability to run some custom aggregates that is possible due to the databases choice that we have done, like analytical database, right? So this capability is not there anywhere till now in DataDog or Jaeger or any other tools. So what we do is this has filtered the list of events. This will create some aggregates on these filter traces, right? So these we see, these are duration we know. Now what is the average duration? How would you like to know? I would like to filter by duration again. Let me see how does the duration profile look like. This is the P99 duration of these filter traces. Okay, got it. So this is a peak and this is we have to convert into it. So it will be like 1 second. It took 1 second. Okay. So if we see some peak here, we would like to again have a latency filter here. Like I would like to see all those requests that are more than 1 second. And I would like to apply, and we got one request that satisfies these filters, like it has service name front end, it has min latency, max latency, and this tag parameters. Now I want to go down triple into it. Now, since we have filtered down into one particular request, we can check everything about that request. Now, as we see, the complete request took 1.4 seconds, and out of it, 1 second was taken by this / customer event, right? So we see that. So now I would like to try to optimize this one. We go down this chart / customer. Now the MySQL query is taking most of the time, like almost 100% of the time, so MySQL query. Now we know what to optimize here, right? So that's how you can explore. You can set custom time range here, and you can see particular trace in that time period. So you can click this and view traces. Got it. So this is the custom time range that you can see during the peak time, right? Similarly, we have other services also. Now this is a service map, or like it gives you the architectural diagram of how the services are communicating with each other. So the front-end service is receiving data from driver service, from customer service, and route service. Okay, so yeah, the front-end service is receiving data from route service, driver service, and customer service. Driver service is receiving data from Redis service. The speed of movement of data is showing you how fast it is receiving data. And the size of the service shows you how much RPS or request per second it is handling. So this route services has P99 latency of 81.9 millisecond, request rate of 8.33 per second. Like every second it is receiving 8 requests from the front end service, and we have an error rate of 0. So this is and the other services are receiving request at a rate of 0.83 requests per second, and then this is the latency profile, right? So this is almost 10 times more. So every request from front, one request to the one request to this application gives you 10 requests to the route service. So this is faster, this is bigger, circle is bigger. Now if here we see some error rates in the service, then this blob or this service should be of red color. If we are receiving 4x's errors in this service, then it will be of yellow color. Now every service is green color here. It means that everything is working perfectly fine. There is no error right now. Okay, so if there is error, it will turn out to be red. So this gives you like an instant, like how the last 1 minute a diagram of your application is looking out to be. You can also select a particular service. If you have too many services, like 30-40 services, this becomes complex to manage. You can go down triple and you can select one particular service, and it will give you a closer view of that service. Got it? Cool. So this is something about SigNoz. We have a user explorer that will give you how much data are we sending continuously. Since we have just installed this in our local host, we have received till now, we have received 61,000 spans, right? So this is the total count of the spans. So every hour we can sort of see it by week and by granularity of every hour, or by daily granularity, and by service you can choose which services sending how much amount of data, right? So it gives you like how much data are you ingesting to the system, right? Later on we'll have some retention period. Like as I told you, it will ClickHouse will store data for the hot storage, or the minimum for a temporary amount of data for like few days and weeks, but it will try to export data to S3 for cold storage, like deep storage, when we have to retrieve the data after 1 month or 2 months or 5 months maybe, right? So here we will provide you a UI that you should be very easy to set this setting up here. Like you just provide 3 days and we'll keep the 3 days data into ClickHouse and disk as hot storage, and after 3 days data it will be moved to S3, and that will be ready to pull up at a later time, and obviously it will be slower. Okay. And apart from that, as we see the application metrics here, P99, P50, P95 latencies, and that RPS is there, top endpoints is there, error percentage is there. We can go to external calls tab. So there are tabs: application metrics tab, external calls, and database calls tab, right? So external calls give you an idea, like if this application is calling external services, then how are those external calls looking like? If my application is calling other downstream services, customer service or route service, and I'm calling external payment channels like PayPal, or I'm integrating with various other vendors via the APIs, I would like to know whether, if my application is slow, whether they are slow or not, or is it or the logic is specific to my application is slow, right? So we'll try to understand those behaviors from this chart. So this front-end service was calling, as we see, right? So it was calling 8081 port and 8083, and 8081 was customer service, and this is route service. So it is calling 2 services, and we can see the RPS, like how many requests per second is this service making to those downstream services, right? And if those downstream services have any errors, you would see it here. So right now they don't have errors, but if the downstream services are throwing up errors, so you will be able to figure it out. So now you know that it is not the error of your service, but it is rather the downstream services or the APIs that are throwing errors, or they are slow, right? So we have external call duration. You should be able to see the time that those downstream services are taking. Like this is the average duration, and this is duration by address. Like each and every API call that we see will be visible here, and we will be able to figure out like which of them is specifically slow. Here we see 8081 is taking 386 milliseconds. That is the customer service. So the route service is 8083 and it is taking 53 milliseconds. So the customer service is much slower than the route service. So if you have to somehow someday you get very slow responses from the customer service, you should, and because of that, your application is becoming slow. So you should be able to figure that thing out very easily. Here we have database calls section. Like if this application is making any database calls like to Python, to MySQL or Mongo database or something like that, we should be able to see these services right now. So as I said, this hot rod application does not actually does the this frontend service does not do any database calls. These are simulated databases, so it is not coming out here. But ideally, if you use OpenTelemetry instrumentation libraries, it will generate data about the database calls also, and you will here find out how many calls to the database are you making and whether those what is the average duration in milliseconds about those databases, whether those databases are slow or not, right? So this is the chart that we see. We change the profile or the time period that you want to see the chat for. You can switch to last 1 hour, like how is the last 1 hour profile like? Again, going to the earlier point, but if you see any spike in latencies, you can go to traces. You got those events. You can filter those out by different parameters, by latencies. You can sort them here. You can click them. You can see the trace and everything. I see. So this is a brief demo of SigNoz. I hope it was useful tool. Let us know about any feedback or any difficulty that you get in installing SigNoz.
Ankit, Arvind has a question here. What does the different colors mean in the flame graph?
Sorry, what are the different
colors mean in the flame graph?
Currently, the colors do not mean anything. These are the default colors that we have used, but we can obviously customize it based on. So we plan to have different colors for errors, the spans or events that have errors, and for different services we can have different custom schemes. So that is possible. Probably we'll go to raise a GitHub issue and we'll try to figure out the logic and do that. But currently there is no logic. This is the default color value that is automatically being shown.
Okay, thanks.
We're open to take new questions if anybody wants to have, or we'll show you quickly how we can do the Python instrumentation, and we'll take up a sample app in Python. We'll go give you a brief overview how to instrument all. So I guess the time is over, but anyhow, I will be doing the recording, and so I will do things here like instrumentation also, and then we can share the recordings also. But if anybody is willing to leave now, they can. Okay, so next
I have one question.
Yeah.
Sorry. Yeah. So like with respect to the database calls that we make, right? Like, do you also have something around like the actual queries that are getting executed, the number of calls being made? For example, if I'm using a Postgres database, right, you can collect like stat information and also like show that. Like, is there any sort of component that gets you, deeper, database metrics?
So the currently what we display is database queries and performance as compared to from an application, right? So as a chart I showed you, it will give you how many database calls is that application making and what is the time taken by the database calls. In the taste diagram, you can see the details like every request, how much time did the database call take, and you can optimize there. Now it comes to monitoring. The databases till now they have not integrated with the metrics and monitoring, they have not are not emitting traces by default. It will happen in the future. Like now, when new databases are being made, they will have tracing inbuilt, but the existing MySQL databases do not have tracing data inbuilt that they emit. They have a lot of monitoring on metrics that they have, and that's probably what you're asking about, I guess. So right now, SigNoz does not ingest metrics data. I have done a POC to ingest metrics data also, and by probably end of next month, we should be able to get all database and other machine related or CPU usage, memory usage, or disk usage related data you can also get from there. So it will be coming in the next month. So OpenTelemetry already gives you the facility to get data from the machine or the application in the database. We can also currently we work only on traces. So whatever metrics we are churning and showing you has been generated by churning traces, the trace data, right? So we have already done a POC, and we'll by end of next month we'll have a metrics pipeline ready, where you can we will be able to ingest metrics data by just giving the config to the SigNoz UI.
Got it. I was also like asking about, for example, let's say I'm like querying the customer query, right? I want to see like, for example, metrics on what are the various queries that applications are triggering, and aggregate them, saying, okay, the count is this, maybe like P50 latency for that query is this, so that I can figure out top end queries which are maybe like taking time and be able to sort of optimize them.
Right. So we already have it, right? So I showed you the list of top endpoints that we have here, right, in this section.
Right, and the aggregation capability that you talked about, is it?
Yes, the top endpoints. So this is in this application has exposed some list of APIs. So these APIs will be here. Right, and any custom thing that you are sending. So these are the standard things that every tech lead knows. Like we monitor the top endpoints, errors, RPS, latency profiles. But anything custom that you want to send, like you want to include a tag like customer type is equal to different, like premium type, then you can always filter it out here. You can select the service. You can type a customer type kind of thing. Okay, and you can type here gold. When you apply filter, you should see the list of traces or this list of events that comply to that filter, and you can choose the duration of P99. You get the P99 profile of that, and calls give you the count or the RPS here. So this chart will give you the aggregates on the filter traces.
Okay.
Cool. We shall move ahead with instrumentation. So let me try doing that. Yeah. So we have given a GitHub repo. We have an independent repo to give some of the sample applications that we can instrument using OpenTelemetry. So this is a sample Flask app, sample Golang app, sample Node.js app, right? So let's take a look at the sample Flask app. Okay, so this is a very simple application that handles a simple query and gives the results back. So it's connected. You need to run a MongoDB server. It has a PyMongo client that connects to MongoDB database. We have /list endpoint that I have simulated here to call to an external endpoint here. It calls to an external endpoint. Simple. It's like a to-do app. Uncompleted list, completed list, done API. So these are there. Okay. So this is a very simple application that we have. In the requirements.txt, we have put Flask is there, PyMongo is there, requests is doing the external calls. Now regarding OpenTelemetry, we can there is a facility to automatically instrument everything in Python, right? Anyhow, you can do instrumentation using the docs given in OpenTelemetry Python. Let me show you that. You can see here like how to install APIs, SDKs, and exporter, like which exporter you want to use. SigNoz uses OTLP exporter. We export everything in the default format of OpenTelemetry. We do not convert one format into another. Nothing needed. Now we have OpenTelemetry instrumentation, and here the name of the package that you use. Like if you have something called, you're using PyMongo, then we'll have PyMongo here, and those kind of things. All right, so you can check out getting started with OpenTelemetry Python, and it will help you, right, how to manually instrument anything that you want, or some sort of automatic instrumentation using the libraries that I told you, like PyMongo, MySQL, and Flask or Django, all these applications. Like, so if you have using Flask, you need to install something, OpenTelemetry instrumentation Flask. If you're using the request library, you will be installing packages like OpenTelemetry instrumentation requests, right? So you can go through this documentation, and this is language specific. Now, for Python, and there is an option to skip installing everything by yourself. Like what we do is that we know that we are using PyMongo, so we have included PyMongo, right? That can also be got by doing a pip freeze. Like if I do pip freeze in my environment, I'll get a list of all the Python packages that we are using, and we can automatically install those. So these kind of techniques have been used to make everything out of box for Python instrumentation. Okay, so OpenTelemetry distro will install like OpenTelemetry API, SDKs, and all the basic set of buckets, lists of all the things that needs to get you up and running. Now, OpenTelemetry instrumentation is the library that has all the underlying packages, libraries, instrumentation techniques that I showed you. And OpenTelemetry exporter, OTLP, is the package that we're using to export our data in OpenTelemetry format or OTLP format. That is what we're telling it to do, right? So now, since we have these insights inside our requirements or TXT, and we have this application, we'll just clone this repository. We'll do git clone, and we'll try to install all the requirements .txt, all the packages inside the requirements.txt, right? So I am inside my repository, okay, and I can do git remote -v. So this is the Node.js app. Sorry. Inside Python, we have Python app, and when we do git remote -v, we see sample Flask app that we have here. Okay, sample Flask app. Now, after doing git clone, we will do pip. We'll do pip install -r requirements.txt. Let me do that. So it will install everything needed, like OpenTelemetry exporter, OpenTelemetry instrumentation, OpenTelemetry distro. Now let us check which packages were installed regarding to OpenTelemetry. We will do pip3 freeze grep OpenTelemetry. So we saw these packages are installed: OpenTelemetry API, distro, exporter gRPC, instrumentation, proto SDK, and semantic version. Now we need to have package relevant instrumentation techniques like Flask and PyMongo and all, right? Now next we go to next step, and we try to install using the OpenTelemetry bootstrap module. We'll do that. Now this will install everything, package specific libraries that OpenTelemetry has. I guess I have many of the things already installed, so that's what it's saying. Now let's get back and see what packages now we have. So we see there are these new packages are there. So apart from OpenTelemetry instrumentation, it installed these packages. So this is ASGI, DB, API, gRPC, Flask, logging, PyMongo, request, SQ3. So I do not have a separate environment, sorry for that. So it has installed a bit more libraries that needed. So it should not have installed WSGI or DB API or ASG API. So if you do in a separate environment, this will install only relevant packages that you are using inside your Python application. Now we know that we have instrumented correctly with OpenTelemetry. We'll try to run. Since now we have not changed anything in the code. Okay. Now the run command seems something like this. Now we have OpenTelemetry set up inside our Python environment, right? We have the packages there. Now, if you append your run command like python3 app.py is your run command. If you append this with OpenTelemetry instrument, it will automatically apply the OpenTelemetry instrumentation and everything needed. You don't need to go to change the code, but you just need to change the run command and it will do that. Okay. What we need to do apart from that is we need to tell them where to send the data that you are generating. So this is the hotel exporter OTLP endpoint is the endpoint where we need to send the data. So it sends data. So now this can be DataDog, this can be Jaeger, or this can be SigNoz. Now, since we have SigNoz running in our local host and SigNoz is ready to receive OTLP data in 4317 port, we can, so this OpenTelemetry instrumentation of Python package will be sent, is ready to send data to SigNoz, right? So we need to add IP of SigNoz here. Where was SigNoz installed? So if you're installing SigNoz in a different machine or different cluster, you need to give the OpenTelemetry Collector endpoint here, right? So since we have installed in localhost, we'll give the endpoint of localhost here, okay? And this is just an environment variable that we have exported here. And the same, there is another environment variable like service name. So you can keep it anything here. Like I have kept Python app, you can keep Python. You can write anything here. I'll write to do app, right? This is the name of my application that I wish to see in my dashboard. Okay. Now, as we see, we have SigNoz running here. We have SigNoz running. This is the OpenTelemetry Collector. Now, here there's a list of ports that it is listening. Okay, so this is the set of ports that this OpenTelemetry Collector is listening. Okay, and 4317 is one of them. So it is listening at port 4317. This is the port for Jaeger receiver. This is the port for HTTP or OTLP HTTP endpoint. This is the port for OTLP gRPC endpoint. Right. So this is for Python. We are using this for Python. Okay, and this is a recommended one. Okay, so OpenTelemetry Collector is ready to receive at 4317 endpoint, and SigNoz is running at localhost, and we have provided that endpoint here. So OpenTelemetry will instrument the application and will start sending data to it. Right now, we are running the application. So we are sending the data here. So this application is now present. It is running at port 5000. So let's have a look at port 5000. Here we have the application to do app, that the Python app that we are running here. Right. So we have the list of to-dos here that I have already played around by generating some load. We have completed tasks. We have all the tasks. So we are playing around with the Python application now. Okay. So this must be sending data to that. So if you see, we have viewed a few APIs. So this must be sending data to SigNoz backend. Now, when we have a look at our localhost SigNoz API, we now have the to-do app application present in the list of applications. This has a pre-internal latency of 1.2 seconds. There is no error rate and the RPS. Since we have just generated a few seconds, there is no big RPS. Okay. Let's have a look at this. Since we just have a few requests, it will not show continuous time diagram like this. But we get the point that we get the data from OpenTelemetry to SigNoz backend in this way. Okay, so let us generate a few more data points and then maybe we'll have a look there. So doing some of the tasks like incomplete, complete, list of all. Now our our SigNoz backend will receive some more data from that to-do app, and when we go there, we now see we have generated 1 minute data here, right? 1:20 p.m. to 1:21 p.m. Okay. Now we have the list of APIs that we have played with. We can select any one of them and go to view traces. We can see the list of traces here from the to-do app. We can click on any of them. We get the list of traces here. Again, everything same like PyMongo. We have the tags like MongoDB, DB, MongoDB, and what is the DB statement that we are using, find to do, right? So you can see everything there. Now we go deeper into this, we should be able to see this external calls, right? So this is making an external, not the front-end service, the to-do app. Okay, so to-do app, inside the to-do app, we'll having multiple calls to external services, external APIs. We get data around that. We are making Mongo calls using the client library called PyMongo. So we are calling, we get the RPS of PyMongo client and the time that it takes to query Mongo. So right now it is taking 2.7 milliseconds. Now these graphs will be evolving like earlier, right? Got it. Okay, so this is how you instrument a Python application. Let me know if you face any issues there. Feel free to raise issues in GitHub and talk about us and give us feedback. We'll try to improve and everything like that. So as we talked, similarly, we have installation steps for different languages. I showed you for Python. We have instrumentation ways to do for Python, Node.js, Java, Golang, everything is there. So you can go and check out these steps and you can instrument your applications and send data to SigNoz. And if there is any problem, let us know in the GitHub repo by raising any issues. Okay. So as told for Java, as a simple for Java application, all we need to do is just download, just clone the GitHub repo, run SigNoz by running installation.sh script. Everything will be installed. Now for Java application, you need to download the jar file, OpenTelemetry jar file specifically. Again, in a similar way, you define the OpenTelemetry exporter endpoint, the SigNoz endpoint, where the port is different, the service name, and you need to specify Java agent to the OpenTelemetry jar that you downloaded and run your application using my app.jar application. That's all you need to do to get that beautiful dashboard that we are showing here. Feel free to get involved more with SigNoz. We have the link to GitHub repo here. We have Slack channel. We have a list of issues. You can feel free to create any issues that you are finding. This performance issue, this bugs, this UI is broken, or anything like that. Okay. So we have some good first issues also. If you want to contribute to SigNoz by developing in React.js, TypeScript, or Golang, we would be, or any of the deployment options, we would be happy to discuss more on the Slack channel of Slack workspace with contributing channel. That's all from me. I hope you got some idea about OpenTelemetry and what SigNoz is and what we are trying to build. Thank you for being a virtual audience. You're wonderful. And so I know it's difficult, but Thank you for being part of it, and we hope to see you all again when the COVID situation becomes better. I'm reachable at ankit@signoz.io, in Twitter and LinkedIn as Ankit Nayan. Feel free to reach out to me.
Thank you, Ankit. Thanks for the great session.
Thank you, guys. So,
Thanks. Bye.
bye-bye. We'll stop the session and we'll upload the recording.